No, on the screen. Okay, it's a pleasure to have Blagoje Oblak, who will tell us about gyroscopic gravitational memory.
Okay, thanks for the introduction, and good morning, everyone. Well, before I start, I'd like to thank the organizers for giving me the chance to speak here. It's a pleasure, and I hope you will enjoy my presentation. So as announced, I'm going to talk about gyroscopic gravity. Oh, you cannot see anything with this, can you? If I, I cannot actually show you anything on the screen here. Okay, that's fine. So I guess, perfect, I have that.
No, it's better if you do it with your finger, because we are always afraid that you get too excited.
But I'm going to touch the screen. Yep. Sure, fair enough. Okay, so then I'll just, do it with my finger, as you say. Yes, I'm going to talk about gyroscopic gravitational memory. This is based on, this is fine, thanks. I'll do it this way. So this is based on this archive preprint, which I recently posted with my collaborator Ali Seraj, who is a postdoc in Brussels. So let me start by just first introducing the subject and in particular motivating it. There are really two broad reasons for studying memory effects. The first reason is that it is by now possible to actually observe gravitational waves. In other words, it's actually possible to see time-dependent metric perturbations produced by various sources in the universe. The typical kind of perturbation that you see takes this rough form, and it's then natural to wonder what are the various measurable implications of this kind of observations. Now, there's a bunch of those implications, none of which I'm going to discuss in detail, but the one I want to focus on is the notion of memory effect. In its broadest sense, a memory effect is the presence of a net offset of certain metric components after the passage of a wave. So if you look at this plot here on the right, you see that, well, initially space-time is locally isometric to Minkowski, so there's no radiation. Then there's some disturbance that passes through, sort of space-time wiggles, and then eventually it all goes back to just being empty space as it was before, up to one key difference, which is that now some of the components of the metric, even though the metric is locally isometric to Minkowski space, some components of the metric have in fact acquired some non-zero values relative to their initial values. And it turns out that this sort of offset typically has potentially observable consequences. Now, the second motivation is more abstract and has to do with the quest for quantum gravity. More specifically, it has to do with so-called asymptotic symmetries of gravitation. Now, broadly speaking, asymptotic symmetries, you can think of them as emergent large distance quasi-isometries of various space-time backgrounds. So for example, if you imagine having an asymptotically Minkowskian space-time with this kind of Penrose diagram, you should think of those asymptotic symmetries as being the symmetries of the system close to the boundary of this Penrose diagram. So here, where you would imagine the holographic dual, the putative holographic dual, to live. Now, again, asymptotic symmetries by themselves are a whole field of study, and I'm not going to discuss them in any detail. But what I do want to stress is that memory effects have been known since a few years now to probe the currents of those symmetries. So to explain a bit what I mean by this, I should stress that asymptotic symmetries by construction do not have standard Noether charges. There's no bulk integral that you can compute that gives you the conserved charge associated with an asymptotic symmetry. By contrast, asymptotic symmetries have charges that are localized on the boundary of space-time, so they are surface charges. And those boundary integrals can typically be interpreted as some components of boundary currents. So in other words, these memory effects typically probe some components of these boundary currents of the putative boundary theory. So those are the two broad motivations for studying memory effects, which you can then think of as observable effects of gravitational radiation, which probe certain fundamental symmetries of both classical and quantum gravity. And so that's why I want to study those. Yes, Monica, a question.
If you mentioned the experimental part, the memory effect cannot be seen with LIGO, right? You have to go to space, or what's the expected, observational?
Well, the most standard memory effect.
Sorry, can you repeat the question?
Yes. So Monica's question was the memory. So she was mentioning the experimental side of the story and asking whether LIGO could ever observe some memory effect. And so I was going to reply that, to my knowledge, the most standard memory effect is called the displacement memory, which is a statement that nearby geodesics tend to move away. I do not know if I thought LIGO could perhaps observe this, but I'm really not I'm really not aware of that particular effect. Actually, I should mention that this is my first time even working on memory effects to begin with, so it's very possible that there will be specific answers to which I will not know the question. So, but sure, I do not know. The point of this memory effect I'm going to discuss now is that it's local on the celestial sphere. So it's really something that you don't have to compare nearby geodesics. You can really do things locally in space, and you will see something potentially. I'll mention orders of magnitude at the very end, and we'll see that it's sort of hopeless, I think, but who knows?
So I think, maybe not lying about this. Yeah, that's what I saw, that you had to set up some experiment in space, and yeah, but at least for the spatial memory, they're hopeful that at least in the next several years, can have something.
So for online people, there's a discussion going on about whether LIGO could in fact observe this.
Or Lisa.
And sorry, Lisa.
Yeah, I thought that LIGO should.
Okay. Yeah. Papers on this typically mention that in a few years' time, it might be possible to observe this. I personally do not know. The experimental side really goes beyond.
So you're going to estimate your effect, but you haven't looked into the actual experimental setups that actually. Well,
there's at the very end, there will be one sort of dimensional analysis argument to explain why it's expected to be really tiny, and that's the best I can say at this stage. But you'll see. So specifically, the kind of memory effect, thanks by the way for the question. The specific effect that I want to talk about is the following. I want to argue that you can use a gyroscope to observe a notion of gravitational memory. So here's a sort of cartoon of the situation. You should imagine having some asymptotically Minkowskian space-time. Here's the Penrose diagram again, where time flows upwards as usual. And in that space-time, somewhere, there lies a source of gravitational radiation. Here, I represented it as some sort of binary system which coalesces, which emits gravitational waves, but it can be something else. And so what I'm going to assume is that there is some observer who is moving in space-time and carrying a freely so the observer is freely falling, and the observer carries a gyroscope. So here the red arrow represents the spin of the gyroscope. Now the point is that as the observer encounters gravitational radiation, the radiation is going to cause the gyroscope to sort of move and along the way precess a little bit. So the gyroscope is really going to change orientation. And as the wave has passed, the observer will notice that the gyroscope now has a slightly different orientation. So there's a notion of orientation memory that the gyroscope is going to carry, and the amount of change of orientation is going to be sort of the agnostic of the kind of waveform that has passed here. So the talk today is devoted to convincing you first that there is such a precession effect and to estimate its magnitude. That's what we're going to do. And in particular, we're going to estimate the orientation memory. As advertised on the previous slide, in particular, we're going to find that there really are some underlying symmetries to the whole problem, because we'll see in particular that the precession rate is in fact a current for so-called dual supertranslations. I'll come back later briefly to what that is. And by integrating the precession rate over time, we'll find that the net memory effect involves a generator of electromagnetic duality in the radiative phase space of gravity. So that's the pitch of today's talk. So now here's the plan. The plan is really simple. I'm just going to first give you sort of the method that we use to perform the computation, and then I'll give you the result.
So this precession effect, of course, already occurs in the gravitational field around the Earth.
Exactly.
So
exactly. Yes.
You don't invoke the memory effect to explain it.
Exactly.
Can you just say?
Yes. So one typical. So I mentioned this. One typical gyroscopic precession effect that you might think of is what's called Lense-Thirring precession, which is the statement that when you have a gyroscope with the source which is stationary and has angular momentum, the gyroscope is going to precess in a sort of dipole law. But the point is the dipole law decays like 1/r cubed. Whereas this effect is actually going to be leading, well, dominant with respect to that. It's going to be 1/r squared effect.
R being the distance.
R being the distance from the source. Yes. Yes. So we were surprised to find that it was a leading effect compared to Lense-Thirring precession. We thought they would be of comparable order, but actually this is a leading effect. And I'll have a few words to say about this, about why, in terms of the metric component, this has to be the case. Even though in practice, of course, well, as you said, you can see this with the sun, for example, in the solar system. So the distances involved with the effect you have in mind are tiny compared with the hundreds of millions of light years that are involved in detecting gravitational waves.
Yes.
So there is this, in terms of scaling, Lense-Thirring precession is subleading, but in terms of actual numbers, it's much, much bigger than what you would actually observe. Thanks.
With respect to what will you see that there is a precession? Because even, for gyroscopes around the Earth, you need to refer to faraway stars or quasars.
Exactly. So that's that's one of the subtle parts of the talk, and that's the first thing I'm going to talk about in the method. Thanks for asking this. Indeed, you absolutely need. The point is that when you talk about the gyroscope that moves, you have to say with respect to what does it move. So indeed, one of the points of the talk would be to build a local frame, a local tetrad carried by the observer, which is tied to distant stars in a certain sense. Now, in easy, simple space-time metrics, such as, say, the Kerr metric, this is easy to do because you have simple asymptotically inertial coordinates. But in the Bondi metric that I'm going to use, this is actually a mess. It's typically very hard to do. So there's going to be a relatively involved discussion of how you can do this in 2 steps. And in particular, as I said, we have to do this in a radiative metric. And then once I've explained this frame building procedure, the second step will be to show you the results, namely the precession rate, and integrating the precession rate will give the net memory. You had a question? No. So yes, before I start in earnest, just 2 more comments. The first comment is that many of the formulas involved are fairly involved. So to simplify some of them, I'm neglecting a bunch of numerical factors. So factors of 2 pi, factors of 2 are sometimes neglected. If you want the actual formulas, please take a look at the paper. And secondly, it goes without saying, please do feel free to interrupt with questions at any point. Okay, so let me start with the method, meaning first explaining the family of metrics in which I want to work and how in those metrics I want to build a tetrad. So those would be asymptotically flat metrics in the Bondi formalism. And as you will see, the tetrad will be built in 2 steps. First, I'm going to build a notion of source-oriented tetrad, such that one of the axes of the tetrad points towards the source. And then I'm going to perform a rotation, a celestially local rotation, such that in fact the tetrad becomes tied to distant stars, as someone online was suggesting. Okay, good. So let me start with the metric. And to introduce the metric, let's start with something completely elementary. Suppose that you just decide to write the Minkowski metric in polar coordinates. So you have Minkowski space, you choose some origin here, and you have a radius that you use here in the metric here. And then you have global time t, and I'm using some coordinates theta a on the sphere. I'm not going to specify which coordinates those are. They can be polar, they can be complex coordinates, it's really up to you. Now, in order to rewrite this in Bondi coordinates, all you have to do is define a notion of retarded time, u, which is defined by this. And in terms of that, the matrix takes the form written here. Now, these coordinates are really going to be important in what follows, so I do want to spend some time explaining their properties. First, you should think of this radial coordinate r as being null, because the RR component of the metric vanishes. And so the region where r goes to infinity is future non-infinity. It's the upper cone here on this kind of diagram. And then on that upper cone, you have 3 coordinates. You have a time coordinate u, and you have further 2 angular coordinates theta a, which label points on celestial spheres. Now, in practice, the actual metric in which your observer needs to live is not strictly flat, but only asymptotically flat. So the way to do this is just to declare that you're going to assume that the space-time metric takes this Minkowskian form up to small subleading corrections. So for example, the UU component starts again with the same -1 as above, but then there are subleading corrections that turn out to contain the mass here. I'll return to the specific form of those terms later. For now, I don't want to stress them. Similarly, there's a correction to the UR component. There's actually a U theta component, which you may anticipate is going to contain angular momentum. Again, we'll return to this. But the one component I really want to stress at this stage is the theta component, because that's the one that really incorporates the most important information. As you can see, it starts with a term which is just the standard metric, but then there's this symmetric traceless tensor CAB, which turns out to be the most important actor in all that follows. So let me say a few words about it. First, CAB, so it's symmetric and traceless, and it's an arbitrary function on future non-infinity. So it has an essentially completely arbitrary dependence on retarded time u and the coordinates on the sphere, except of course it has to be smooth. And it's known as the Bondi shear or asymptotic shear because it literally describes the asymptotic shear of outgoing non-geodesic congruences. Now, in particular, that guy turns out to contain all the information about radiation even in the bulk. Indeed, by definition, the newest tensor is the time derivative of the shear. So I'm going to write that as C dot. And saying that that contains information about radiation is really the statement that whenever there is some source of radiation here in the bulk, well, there is radiation escaping to non-infinity if and only if C dot is non-zero at that particular point at non-infinity. So that's really what the news is, and it's really the most important actor in all that follows. Now, I do want to spend a bit more time explaining you some of the properties of this metric because they're going to be important later on. So let me give you a bit more details. First, as I said, this component starts as in the Minkowskian case, and in the first subleading 1 over R correction turns out to involve this quantity m, which happens to be a function on future non-infinity. So it's called the Bondi mass aspect, where the word aspect stresses the fact that it's local on non-infinity. So you can think of it as a sort of energy density at infinity. In fact, sort of the current conjugate to BMS supertranslations, if you know what that means. By the way, of course, there are, of course, further 1 over R squared, 1 over R cubed corrections here, but here I'm not writing them because they're not going to. Actually, if you want to do the computation I'm going to describe and make sure that the tetrad is orthogonal and everything, you do have to go deeper in the 1 over R expansion. But here, for the sake of the talk, I'm not writing those down. Then there's similarly a 1 over R squared correction here. We don't care about this. Now let's look at the U theta term. As I said, you expect, yes?
If there's black hole merging going on inside, is M should be thought about the mass of the 2 black holes?
So the question is, if there's black holes merging in the bulk, should they think of M as the mass of the 2 black holes? I guess that's the order of magnitude, but if they're merging, then they're emitting gravitational radiation. And so this is going to become explicitly time dependent. I'll write that down in a second. Actually, here it's going to appear. But thanks for the question. It's a good point. So let's talk about the angular momentum term. Now, as I said, the U theta component you might think contains information about angular momentum, and it does. But actually, the leading component is a derivative along the sphere of the shear tensor. And it's only at order 1 over R that angular momentum actually appears. And just like the Bondi mass aspect, it's also a local function on future non-infinity. Now, what I want to stress here really is that this derivative of the shear, in fact, in terms of order, oh, what happened? Oh, I touched the screen. Yeah. Oh, I'm sorry, I touched the screen. Okay, fine. That's right. Okay, so this guy is actually much larger, of course, than 1 over R times the angular momentum. And this is really sort of a feature that we're going to carry around us for the whole duration of the talk. In fact, as sort of it goes along the lines of your question, the effects of shear turn out to be dominant, at least in the 1 over R expansion, in front of the effects of angular momentum. And you will see that this EBCB term is going to sort of cause us some trouble later on, and we'll have to deal with it in due time. But for now, just notice that there is this sort of scaling relation here. Now, of course, I have presented so far these functions, Bondi mass and angular momentum, as if they were arbitrary functions on non-infinity, but that's emphatically not the case. In fact, their time dependence is entirely constrained by the news, and in fact, they satisfy so-called balance equations. Now, these equations are, again, relatively involved, so here I just want to give you the flavor of how they look like. And so in particular, what you find is that the time derivative of mass is minus the nu squared. So answering your question, if there is some source of radiation in the bulk, what's going to happen is that the total mass of the system is actually going to decrease. This is a statement, as you would expect, that radiation carries some net energy. So this has to be the case. Then there's a similar balance equation for angular momentum.
And after relaxation, you just get the mass of the 2 black holes.
Sorry?
After relaxation.
After relaxation, it does, exactly, yes. Yes. That's why they're called balance equations. The balance between, I guess, bulk energy and the energy that escapes. That's how you can think of it. And similarly, for the angular momentum, there's a balance equation of this kind. It's a bit more involved because there are indices, but actually that equation is going to be useful later, close to the end of the talk. So I'm going to just have a very short annotation for it, just so you remember when I mention it. I'll write this as L dot, which is roughly bilinear in the shear and the news. So it turns out that this is an equation we're going to use. The one thing I do want to stress again is that everything is determined by the shear. Provided you know the initial condition at some fixed initial time, everything evolves according to the knowledge of the shear, which you can think of as a sort of external current, which is God-given, if you will. And the rest is just fixed by initial conditions for the mass, the angular momentum, and the infinity of further functions that appear here in this expansion, which I haven't written down. So that's the family of metrics in which I want to work. And
the shear itself, of course, satisfies its own equation.
Sorry?
The shear itself, of course, satisfies its own evolution equation.
The shear?
Yes.
No, it doesn't. That's the whole point. That's exactly the point. The shear is the only quantity that has an arbitrary time dependence. Actually, this is not quite true. There typically are certain fall-off conditions that you impose on shear. It has to decay at least as fast as, I guess, 1 over u to the cube, I think, as u goes to infinity, or u to the 3/2. But so there are these kinds of conditions, but it's only fall-off conditions. There's no condition on really how it depends on time in the bulk. You can think of it. There's sort of a Hamiltonian perspective on this. You can think of future non-infinity itself as a sort of null limit of a Cauchy surface, and it's clear that you have to impose some information on the Cauchy surface itself to determine the whole time evolution of the system. And it turns out that here you're sort of packaging the whole information there into the shear plus initial conditions in time. That's really how I can think of it. Thanks, it's a good question. But shear emphatically is not constrained. So those are the metrics I want to, but is this because there's a chat? No, okay. Maybe there's a question.
No, yeah.
Was that some sort of, so like, can I use the Einstein's equations to say something?
Sorry, can you please repeat the question?
I mean, if I have, I mean, can I use the Einstein equations to say something about the shear tensor?
No, actually, those are Einstein's equations. That's how you derive those.
Okay.
That's the whole point. In fact, what I'm writing here is the on-shell form of the metric. It's a metric that already solves the vacuum, right? So this is all vacuum. It's the vacuum Einstein's equations, and this is a consequence of Einstein's equations. Written here in very, very sort of primary school form, but that's really what it is. So no, I'm giving you everything there is on shell. So those are the metrics we want to consider. And so what I now want to do is to say, well, we have an observer somewhere in space-time who's looking at this sort of source of radiation, and I'm going to assume that the observer is really falling. So there's an observer at a very large distance from this source who wants to observe what happens there. So in particular, the observer follows some geodesic, and you can solve the geodesic equation for that guy in powers of 1/r. So you can perform this asymptotic expansion at large r, find the various terms, and in doing this, you're going to have some integration constants which you have to fix. Throughout this talk, I'm going to fix those integration constants by requiring the observer at infinity to be asymptotically at rest. So in other words, at infinity, the observer just sits in terms of boundary coordinates in front of the source and doesn't move. Of course, this is going to be modified by subleading 1/r corrections, many of them, in fact, but at leading order, we're just going to find that. That's, by the way, just a simplifying assumption. It doesn't really affect the results, I think, that much, but it's much easier to do computations that way. Now, in practice, the observer carries a gyroscope, which you can think of as a sort of measuring device that the observer is going to use to see what radiation does. So the observer needs to measure the orientation of that gyroscope with respect to some reference frame. So what frame could you choose? Well, given abstractly the form of boundary coordinates, the most natural frame you could imagine is a source-oriented one, meaning a frame shown here, where one of the axes, say this one, the horizontal one, really points along the direction of the source, and then the other ones are fixed by orthogonality. That's the simplest frame you can think of, but we'll see that there's a complication in doing that. But for now, let's just proceed with that one. So we have a zeroth element, a radial element, and angular elements, where the zeroth element coincides exactly with the proper velocity. That's how the observer fixes what they call their proper time. Then the radial vector asymptotically has to go like d over dr, but then you have to remove this minus d over du to make it orthogonal to E0. And again, I stress this is only true at large r. There's a number of subleading 1/r corrections to these expressions, which you have to work out by solving the geodesic equation, requiring that all this is a Lorentz basis and so on. So you can do this. And then similarly for the angular components, well, those turn out to scale like 1/r times a choice of diet on the unit sphere. So you choose a diet capital E, you have the leading behavior of those guys, you choose it at will, by the way, and then you can solve perturbatively 1/r to find exactly, well, to find perturbatively those expressions. So that was sort of the first computation that we did, and I'm not going to give you the result here because it's not particularly illuminating, but you can do it. There's one point that I do want to stress, although. So the point I want to emphasize is that when you solve the geodesic equation with this initial condition, you find in particular that there is a non-zero angular velocity, which happens to scale like 1/r squared and involves this term dBcd. You may remember that that was the leading term of the u theta component of the metric. Now, what that means is that whenever there is radiation, whenever there is some shear propagating in space-time, well, the radiation is going to cause the observer to rotate around the source with a non-zero angular velocity. And that rotation turns out to be a huge problem for what we want to do. So let me explain why this is a problem. The problem is that when you use a source-oriented frame, well, by construction, you are source-oriented at all times. So if you happen, for any reason, to be rotating around the source, well, of course, you're going to have to also rotate your frame accordingly. Now, that, by the way, would also occur in Minkowski space. It's trivial. If you're pointing to the origin and you happen to rotate, well, you have to rotate your axis. But the point is, in Minkowski space, there's no radiation, so you could just choose to be at rest and use that as your frame. Whereas here, we've just shown that radiation forces you to rotate at order 1/r squared. And actually, that sort of ruined our lives for a few months when we were doing this initially, because it turns out that the precession effect we're going to find is going to be of the same order as that 1/r squared angular velocity. So you have to find a way to somehow remove that, in a sense, spurious rotation, which doesn't it really does, it's not a diagnostic of radiation, it's just a diagnostic of the fact that you happen to be rotating around the star, around the source. So what we're going to do is just to choose some distant stars, which we're going to take as a reference point, defining a new frame. So if, for example, here, you would choose a distant star here on the right, which is initially aligned with the source, and then you would have other stars to define the other directions, and you pick them once and for all, and use them as reference point. So that means, for example, that when you've rotated a certain amount, you're going to have to compensate this rotation of the frame by some other rotation here of your frame. So that's really what you have to do. In practice, abstractly, what this means is that if you call E the source-oriented frame, then you have to perform a celestially local rotation, R of theta, such that you map it on a new frame, F, which is now oriented towards stars. And in what follows, that's the frame we're going to use. In particular, we're actually going to use this rotation matrix for simplicity to coincide with the identity at the initial location of the observer. So if the observer is initially located here at time 0, well then they choose a source-oriented frame, and then they look for stars which happen to be oriented in the same way initially, and then there's some time evolution that's going to make them move, and then they're going to perform these celestial local rotations. This turns out to be really crucial because that's going to allow us to see precession as a genuine diagnostic of radiation. And so now we're going to write the gyroscope spin in terms of this basis, in terms of these sort of vectors, and read out the precession. Before I move on, there's just one sort of technical note which I want to make, but for the people working on asymptotic symmetries and a bit familiar with this, there's something weird we're doing here. Typically, when you deal with asymptotically flat spacetimes, you just assume that there is one notion of infinity or an observer located there, and you use one of our expansions. But here we're actually saying that we are an observer located on sort of something that's near the celestial sphere, but then we also assume that there are even much more distant stars at strictly infinite distance, which we use as a reference. So there's sort of a separation of scales we're assuming here. If someone knows if this has ever been done in the literature, I'll be interested to hear. We have never seen it, so we had to make it, and that's it. At least mathematically, it seems consistent, but we're interested to have comments. Anyway, that was an aside. What we're now going to do is use this frame F tied to stars, write the spin in terms of that frame, and write the precession of the spin in terms of that frame. So let's do this, provided this button works. Okay, so that's the second part of the talk. Are there any questions, by the way? Even online? If there are no questions, that's fine.
So if you just take a stationary clear black hole, how would you see the position effect, the Lense-Thirring effect in your formalism?
You would see it exactly like this. So on the next slide, I'm going to explain in terms of the spin connection of the frame, how you can compute the actual precession velocity. And so what you would do in the curved black hole is that you would do exactly this. You would pick a frame tied to distant stars, and you would compute the spin connection, and you would find that there's an order 1 over r cubed precession velocity, which happens to have this beautiful dipole formula that you know.
So how does the new tensor look like for the stationary black hole?
No, there's no news for the stationary curved black hole.
It's 0.
It's 0. It's strictly 0. So all the effects of the news and shear are completely washed out. When they're not washed out, they just do not exist. Again, that was our surprise. Our surprise was that we thought that the two effects would be sort of similar order, but actually the news is really dominant in terms of one of our expansions. So if you were to do an experiment in this room where you somehow make gravitational waves, at 5 meters distance, this would be the dominant effect. But in practice, that's not what we can do. So
this 1 over r squared is just because the waves are spreading out in spheres, right?
Yes.
So you're just saying that this is something this gyroscope gets a kick from radiation, so you can even make it more leading by focusing the radiation if this is possible.
Fair enough. I had not thought of that argument, but that's true. Probably that's one way to think of it. Fair enough. No, true. Okay. So I don't know if you guys heard online. The statement was that you're expecting the 1 over r squared behavior based on sort of conservation of energy. And yeah, that's a good point. No, I hadn't thought of that. Maybe that's sort of an intuitive reason. Anyway, we're going to see the results. So I want to do two things. First, I want to give you the result for the precession velocity, and we'll see that the precession rate is sort of a dual mass aspect in a certain sense. And then I'm going to integrate the precession rate to read off a notion of orientation memory. So first, to explain how we compute the precession in the first place, let me just set up the problem. So what we have is a freely falling gyroscope with some spin s. The spin is orthogonal to proper velocity, and it's parallel transported along the geodesic that it follows. So this is the equation that it satisfies.
So going back to this bit, couldn't you just formulate then everything just in the space-time with the shock wave and looking at the orientation before it crosses the shock wave and after? Wouldn't you get the same result?
Maybe I would. I really do not know. I really do not know. Maybe I could do this. You mean in that case, I would no longer have to use bonding coordinates? You say I could really use a literal shock wave in sort of near Minkowski, so you have sort of.
You know that an observer when it crosses the shock wave, like his position will jump. This one I already know. Maybe there's also something similar here for orientation.
Okay. I do not know. This I really do not know. It's an interesting question. Thanks. No, I don't know. So the setup we have is a spin vector, which is at the position of gyroscope, and it's parallel transport along its position. So this is sort of the trivial gyroscopic dynamics. But in practice, what we wish to do is to write this spin in terms of a local frame, which is tied to distant stars. And the frame, of course, is generally not parallel transported. So the whole point is going to be to see how this frame, this particular frame, is not parallel transported, and that's going to give us the spin precession. So specifically, when you plug this equation back into this parallel transport equation, it turns out that you find this kind of equation of motion. Now, here what I'm writing as S dot is the derivative of spin with respect to proper time of the observer, but at infinity, the observer's proper time coincides with the retarded time u in terms of bonding coordinates, so S dot is really the same as before. I mean, the dot means the same thing as before. And then on the right-hand side, you find this anti-symmetric matrix omega ij, which is sort of the precession rate acting on S. And so what you conclude from this is that knowing the spin connection of this frame determines everything you need to know about the spin precession rate. And so that's really our goal. Our task is to just compute that spin connection. Now in practice, because we're using bonding coordinates where it's much more natural to first use a source-oriented frame, we did this in 2 steps. We first computed the spin connection of the source-oriented frame. Again, we did this at large R, so there's a bunch of 1/r expansions and everything. And then we compensated this sort of spurious rotation of the source-oriented frame by applying the rotation R, which now contributes to the spin connection as this sort of gauge transformation law. And in particular, in fact, you see that there's this inhomogeneous term in the transformation law, which turns out to be the key term that actually cancels the spurious rotation that you would see because of the source orientation. So really, this is the key term that in the end gives you the right result. So again, this is sort of a long computation in which I'm not going to go at all. I'm just going to flash the result. There's just, I guess, yes, there's just one thing I want to mention, which is related to your comment. So if you were to do the same exercise in the case of a stationary metric, you would find from this the Lense-Thirring precession effect. So, oh, by the way, for those who don't know what Lense-Thirring precession is, it's really the statement that when you have angular momentum in the bulk, you take a gyroscope, we'll find that the gyroscope precesses, regardless of, there's no radiation. It's really just a stationary metric with angular momentum, and the gyroscope is going to precess in a certain way. So this includes the Lense-Thirring computation, but we'll see that it modifies it actually by an overlaid dominant term. So to explain the result, I'm going to just rewrite all this in terms of a vector omega. So I'm going to dualize this into a vector omega k, such that this spin precession equation takes this vector form in terms of the standard cross product of Euclidean space. And then the result is going to be spelled out in terms of 2 tangential components of this vector omega, tangential to the celestial sphere, and 1 radial component which goes along the direction of the source. Now, it turns out that the tangential components go like 1/r cubed. So for all practical purposes, they're actually negligible, subdominant with respect to the leading contribution, which goes like 1/r squared. That's actually our main conclusion to begin with. The main precession takes place around the axis of radiation. So if you have a source here, and you're looking at gyroscope here, it's going to precess in this plane. And the amount of precession is given by this particular expression here, which has in particular, as you can see, a linear term involving what's called the dual shear, given by this expression in terms of the Levi-Civita density. And then there's also a quadratic term appearing here, which involves the Null tensor. So that's the expression we have, and in what follows, I'm going to spend some time discussing some of its properties. The first property that I want to stress is that we can actually do the same computation, of course, in terms of the source-oriented frame. There's nothing stopping you from doing this, and in fact, that's what we initially did. If you do this, you will find a different precession velocity, omega prime, which turns out to have tangential components that fall off like r to the -2. So they're of the same order as the radial component. And the radial component itself coincides with this up to this 1/r squared dB CAB term. This is again the same term I mentioned earlier, the same term that causes the rotation of an observer as a result of rotation. And so again, the way to compensate these terms is to perform this rotation that gives you a tetrad which is oriented toward distant stars. You had a question? No. Okay. So that's why we perform this rotation in the first place. In particular, This is actually crucial because it allows you to use this as a diagnostic for the presence of radiation. By this, I mean that if you look at this expression, it turns out, and again, I'm not going to show the computation in detail, it turns out that you can rewrite this whole thing as the time derivative of some components of angular momentum plus something that involves a news. So this means, let me just mention. So what this means is that in a stationary case where you have zero news, this term vanishes, angular momentum is constant, so this whole thing is zero. So in other words, at this order, there is no precession without radiation. There's literally a synonym, or sort of an equivalence, between having this kind of precession and having some radiation. It's really a diagnostic of the presence of radiation. And I stress that this is because we use the star-oriented frame. If it was source-oriented, we have this extra term, which would completely ruin the interpretation.
So the Lense-Thirring effect is for the source-oriented frame. It doesn't exist if you use
Exactly. Yeah, sorry, can you repeat, please? No, the effect exists for star-oriented frames.
The Lense-Thirring effect only relies on the fact that you're using source-oriented frame as opposed to distant stars.
Yeah, but again, in a typical, so you see, in the Kerr metric, CAB is 0.
Yeah.
So you wouldn't even have this term to begin with. If you look at Misner, Thorne, Wheeler, the exercise where they ask you to do this computation, it's even much simpler. There's no question of this having this term.
It means that the next order in one of the output, that's what you is saying.
Exactly. So that's this comment here. It turns out that if you do this computation, you can recover Lense-Thirring as well at order 1 over R cubed here, which I haven't written down. So it exists.
So that thing, the omega A, this is not Lense-Thirring then?
I think that actually contains some Lense-Thirring contributions as well. But my point here was, above all, to stress that this is smaller than this. That's it.
Sure.
That's it. In principle, Lense-Thirring precession is given by this dipole formula. So in principle, you know, depending on which location you are on the celestial sphere compared to the, the angular momentum, which is the source, you might have, in general, you would have all 3 components of the precession velocity which are turned on, and they would all be turned on at order 1 over cube. So yes, you should, it contributes here, it contributes there, but it's subleading with respect to this. Yes, actually, yes, so sure, there were 2 questions, go ahead.
Yeah, I just have a simple question. Why do you call them the spurious terms? Because they are like, in the particular frame, they will measure these terms, right? If you
Yes.
the frame.
Yeah.
Why do you call them spurious? It's like,
Well, they're spurious in the sense that they're not the terms I'm interested in. They are an uninteresting rotation that I do not want to take into account. Of course, you might actually be interested in, performing an experiment where you can somehow measure your own sort of kick that you get from radiation. Actually, maybe there are even some computations in literature that do focus on this. So that's, by all means, an interesting thing, but for us, it's sort of uninteresting.
okay, so what you are saying is if you just want to know the effect of the radiation passing through, you need to remove those.
Yes, that's it. Yes. Andrea, you had a question?
Yeah, so this effect has to do with super translations, which are not different.
I'll get there in a second. That's the next slide.
Okay.
That's the next slide. So indeed, so the question here was, I don't know if people heard, this effect has to do with dual super translations, and that's actually what I'm going to talk about now. So I do want to spend some time saying a few more words about this expression here. So it turns out that this quantity is known in the literature on asymptotic symmetries. In a recent paper by Freidel and Franzetti, it was called the covariant dual mass. The covariant dual mass aspect. So I want to tell you a few words about what this is. Well, the first thing you should know is that it has nothing to do with mass. It's by no means the notion of mass, because as we have seen, the mass is a current for super translations of non-infinity, whereas this, in fact, is a current for so-called dual super translations. Now, dual super translations, you can think of them as a sort of complexification of super translations. That's how Parati thinks of them. Another way to think of them is that extra charges that you can see from the Newman-Penrose formalism, that's how they were derived here by Godasberg and Pope. So as Andrea was pointing out, those are not actual diffeomorphisms of space-time. They're sort of much more abstract symmetries. And to my knowledge, there's no consensus as to what you're really supposed to do with them. Should you think of them seriously, or should you just think of them as a coincidence? I personally have no opinion. Well, actually, I do have an opinion. I think they're actually crucial if you want to talk about dressed states. But that's way out of this talk. But indeed, we can talk about it. But if you want to talk about dressed states, they're crucial, and you have to put them in the symmetry group.
My question was actually about historically, let's say if boundary conditions were imposed that would rule out dual super translations. Originally, there was some issue about the factor of 2 that was fixed by making the boundary conditions more constrained. Yes. And then this ruled out dual super translations, but then it was pointed out by Gyroscopic brothers and Paul and so on, that actually you can alternatively not relax not constrain the boundary conditions and then have these dual super translations. But so I'm wondering, so if you do impose stronger boundary conditions, then you would not view this gyroscopic memory effect. Are you saying that if this is really an observable quantity, then you give
you have to do some exotic boundary conditions.
that these dual superpositions actually exist and are real symmetries of nature, even though they don't come from a real different one. Okay. So there are several questions. First, I would not necessarily use this as an argument to claim that those are a real symmetry of nature. I don't know that. What I know is that this is the result that you find from doing the computation, and in principle, this should be zero. If you actually use, later on, I'm going to talk about the memory effect, where you can use the balance equations to rewrite it in a clever way. Actually, it's essentially, there's actually a term there that's really just spin memory. It's the spin memory effect, which was found long ago, plus an extra term which happens to occur here, which has to do with duality. So in that sense, this is not particularly exotic. It happens to coincide with these dual supertranslations, but in principle, you don't have to think of them as proving anything in terms of dual supertranslation. In terms of the fall-off conditions, I remember the discussion, although not the details. I have not assumed anything exotic about the boundary conditions here. I might want to assume that there exists no gravitomagnetic monopole, that's fine, but that would only imply that the average value of this over a celestial sphere vanishes. But locally, at a point in a celestial sphere, there's nothing that prevents this from existing. And here I'm working at a point in the celestial sphere. So I think in principle, you would imagine this to be non-zero.
You're not really on the celestial sphere, right? You're just far away.
Yeah, absolutely.
I think it's also way more.
Yes, true. But typically, this quantity, up to the 1/r², this is a function of u and theta. It's a function of the celestial sphere. And you might wonder, is it zero or non-zero given some constraints or boundary conditions? What I'm saying is that with standard boundary conditions, this may well be non-zero, except that typically we'd assume the integral of that over a sphere to be zero, because we assume there's no gravitomagnetic monopole. Okay? Does this?
You're saying that there are no sources which would create, there could be no sources which actually make this non-zero?
No, I'm saying that there are no sources that create this such that it has a non-zero average on the sphere.
There is no zero mode.
You can have a function which sort of wiggles on the sphere, but such that sort of it's parity odd, if you will. So whatever happens here compensates whatever happens there, and the average is zero.
Okay.
But locally, it's non-zero, which is what it is. So, and that's actually exactly why I'm not trying to make this into a claim that this is an important fundamental symmetry of nature. I don't know that. I don't know if magnetic monopoles really can see them. So I'm just taking this as the result and saying what it relates to. Thanks for the question. Right, so as I said, I was explaining the name, covariant dual mass. So I said why it's a dual mass. I haven't said why it's covariant. Well, it turns out that if you remove this extra term, this is also a notion of dual mass aspect, but it's not covariant with respect to what are called Weil BMS transformations. So if you take the BMS group along with local conformal transformations and Weil transformations, it turns out that this particular object, this particular combination is covariant in the sense that its transformation law under all these transformations has no central extensions terms. In this paper, they call them anomalous terms, similarly say to the Schwarzschild derivative and that kind of thing. Well, here it's really that thing that happens. Finally, there's one thing I should mention, which sort of gives you an intuition for why this had to be related. So no, we're talking about the gyroscope, and we happen to find something that apparently has to do with gravitomagnetic dual terms. So you might wonder why. And the reason really is that when you decompose, say, Riemann tensor in Divide tensor in electric and magnetic components, the electric components typically tell you the deviation of the distance of geodesics, whereas the magnetic components tell you how the geodesic congruences tend to rotate, to change orientation. That's what we're seeing here. So it sort of makes sense that for a gyroscope, where we're computing the change of orientation, we do find gravitomagnetic terms. Okay, so that was everything I wanted to say about this precession rate. I have no clue how I'm doing it with time. How much time do I have? Well, actually, I have 15 minutes. No, wait.
Yeah, good 15 minutes.
Oh, good, fine. I'll have that. So I finally want to talk about the memory effect that follows from this precession rate. So again, to set up the problem, we have this sort of precession equation, and I stress now that the precession only occurs during a radiation burst. So you should imagine having this situation I plotted before, and the precession only takes place during this period. There's no precession before, no precession after. And so it makes sense. Oh, by the way, you can now think of this, I wrote metric perturbation initially, but you should really think of this now as writing the asymptotic shear as a function of time. Now, given that we know this, well, we can just solve this equation and see what it does. So if you solve this formally, you find that it's a time-ordered exponential of the angular velocity acting on the spin. But in practice, you have to keep in mind that this angular velocity vector is tiny. It's a 1/r² effect. And in order to expand this exponential, if you want to go, say, to second order, you would have to include order 1/r to the 4th terms into omega, which we have not computed. So actually, the only reliable order at which you can expand this is just the first non-trivial order, which really tells you that there's an infinitesimal rotation of this form that has actinal spin. So our task is to compute that integral. Well, let's just do it. The net angle, I'm going to call it theta, is an integral over time of the precession rate, which was 1/r² times this combination of shear and news. In principle, you could stop the discussion here and say, okay, well, that's the net memory effect. Now deal with it. That's it. In practice, it's common in the literature, and it's really illuminating to sort of massage this expression so as to sort of highlight the effects of, well, the effect, highlight the appearance of various interesting symmetries of the gravitational phase space. And so that's what I'm now going to do. So, and by the way, when I say that's what I'm now going to do, again, all the equations are going to be sort of given in a very intuitive manner, and I'm not going to be completely precise, but I do want to give you the flavor of the computation. So the flavor is the following. You start by saying, let me use the balance equation for angular momentum. If you recall, I mentioned earlier on in the talk that the angular momentum has a time derivative, which is roughly this bilinear combination of shear and news. So it turns out that you can use this back here to rewrite this first term in a sort of clever way, which happens to be this one. So let me explain what this means. Here, what I'm calling L minus is the parity-odd scalar component of angular momentum, meaning that if you decompose the angular momentum on the sphere in these terms, this is the L minus term, which is parity-odd here. And then what I'm calling J minus is something I'm not going to write down explicitly, but it's sort of an analogous parity-odd term for the flux. So it's non-linear. It's a non-linear term that contains the news step. So it's really something dynamical. You can think of it in a sense. You can think of this integral as sort of dynamical phase in the language of geometric phases, but that goes well beyond the subject of the book. So that's the first step. And then the second step is to invert this relation using the propagator on the sphere, a sort of inverse of the Laplacian up to this vector of 1/4 pi. You plug that back here, and then there's a clever way to rewrite this, which takes the form written here. So now let me explain what these letters mean. What I'm calling Q, by definition, is a charge associated with an area-preserving infinitesimal diffeomorphism of the celestial sphere. So in some portions of literature, you would call this a superrotation, especially by Geoffrey Compère and others. So you can think of this Q as a charge for superrotation, and delta Q is just the difference in the initial charge and the final charge. So this term generally measures this kind of offset, if you will, before and after the passage of radiation, except that this guy is actually sensitive to the offset of angular momentum. Then this flux term here is a similar term, but where the sort of the angular momentum is replaced by the flux of angular momentum, and it's integrated over time. So again, this is a linear term in metric data. This is a non-linear term. And in fact, this sum, delta Q plus F, is known in the literature because that happens. So yes, F, as I said, is the flux. And this sum happens to be what's called the spin memory effect. This was shown by Pastersky and Strominger and Zhigoyedov. And so this first term just shows us that this orientation memory is nothing but spin memory plus this extra term. And so the question that remains is to understand what is this guy, the news times the dual shear. And this is really the last question that I wish to address. And to answer it, what we have to do.
Can you say what is spin memory in contrast to this memory effect for gyroscope? It's like spin.
Yeah. So actually, in our paper, we even have. Yes. So I can say the first thing I should say is that if you limit yourself to small gravitational disturbances, this is a nonlinear term. This is a nonlinear term. So the only term that you will actually realistically see is this one. All the other ones are small. And it turns out that if you focus on that term, so well, I can even say differently. Let me go back. Yes. If you look at this term here, that was the precession rate. If you forget about this nonlinear term, you would imagine this term to be the dominant term. And if you just rewrite the whole thing, you recover the memory effect, the spin memory effect. That's what I said. But what you can even see is that the spin memory effect, in the way it was initially derived, was a sort of delay. Well, it was a change in the interference pattern of photons going around the loop, which is located somewhere far away from the source of gravitational radiation. And what you saw was that as you perform interference experiments for those for light, you would see that the passage of radiation would change the interference pattern. There was a delay, there was sort of a difference in the time it takes to go in one direction around the loop and in the other direction. And it turns out that abstractly, the value of that delay, if the buttons deign to work, the value of that delay was essentially this delta Q plus F. And I believe it was called, well, maybe you, Andrea, know this better. I believe it was called the spin memory effect precisely because it is sensitive to this sort of superrotation effect. But of course, the terminology is very suggestive because we're talking about the spin of a gyroscope. So we do not know at the moment if there is a deep reason why we find the same thing for spin memory and, well, for gyroscopic memory and spin memory. One thing you can say—
just miss also the effect that's not taken track of.
We've thought about that, but we don't think so. We've repeated their computation. We don't think that's the case. On the other hand, actually, if you ask, I'm not a specialist in gyroscopes, but if you ask people who know a bit how modern gyroscopes are made, they're actually made with Fabry-Perot interferometers, with genuine little photons that go in loops in different directions with an interference pattern. So they have pretty much done something very, very similar to this computation. So, I do not know, but I would like to have a deep explanation for why we find something similar but not quite the same, but I'm not sure. Notice that the formalism is completely different. They never talked about a tetrad. They're never comparing anything to a tetrad that you carry. So, and also, by the way, their observer is not freely falling. They take an observer who is fixed. Maybe that does actually change things because we've computed the spin connections for a fixed observer, and they are different. They're even leading terms that you do not see here. So there are sufficiently many differences that it's a bit puzzling, but we do not know any deep reason for why that's the case. Thanks, it's a good question. Okay, so as I said, we recover something that seems familiar, spin memory effect, but we find an extra term. Yes?
In this analysis, there was a scalar analysis, the dual covariant mass didn't show up.
Sorry, I didn't get the question.
Covariant mass didn't show up, right? They never talked about
you mean in the spin memory effect? Yeah. No, they never did. No. But I mean, the expression is really the same all the way down to the form of this superrotation. It's really the exact same expression. So, there's a relation, except that they just talked about superrotations. They didn't talk about anything dual. Okay, finally, let me say what this C dot C tilde term is. So to sort of understand it, you have to go back to what's called the radiative phase space of gravity at non-infinity, which again, I'm going to sort of flash you very quickly. So the statement is that if you look at this future non-infinity, which you think of as a Cauchy surface, the canonical variables on that surface happen to be the shear, CAB, and the Nu's tensor. And now I'm going to call the Nu's tensor N to stress that as a canonical variable, it's really independent of the shear. And then the symplectic form in terms of those guys happens to be this integral over future non-infinity of delta C towards delta N. Now the question is, how does the canonical generator for local duality transformations written here look like, given that this is a symplectic form? So local duality maps, for example, C on C tilde with some local function, the celestial sphere, and the same thing for N tilde. Well, it turns out that if you plug those, if you find the canonical generator for that, what you find is this kind of expression. And as you can immediately see, this is really the same expression as this one, up to the fact that here we happen to have an epsilon function, which is a delta function at the location of the gyroscope. So in short, it seems that orientation memory can be written as a spin memory effect plus a local duality generator. So that, in a sense, is our final, I guess, slogan for what orientation memory should be, how orientation memory should be seen. Monica, you seem to have a question.
Sorry, I just missed one point.
Duality, local duality is defined by this. You map the shear on the dual shear, where C tilde is defined with this epsilon A, B, C, BC, I guess.
Is it the symmetry of Einstein's equation?
It's a gravitational analog of electric magnetic duality, whereby you rotate the electric field into the magnetic field. So here what we're doing is rotating the electric components of the Weiss tensor into magnetic components of the Weiss tensor, and it so happens that in terms of these functions, it takes this form. That's really how you should think of them.
It's not a true symmetry, right?
It's not a true symmetry. No. And in particular, as far as I know, there exists no manifestly duality invariant formulation of full GR, right? It's only known.
Yes, there are even no-go theorem for at least.
Okay, exactly.
Local construction.
Yes. So I'm just saying that if you perform this transformation on radiative phase space, that's what you find.
No introduction, just because
Sorry, what did you say?
You said it doesn't exist an action which is invariant.
Right. Okay.
No, you said formulation, right?
Yeah. Okay. Fine.
Well, when I said duality invariant formulation, I mean the things that Noether does. You know that he has these duality invariant, for example, in electrodynamics, you can do this.
Right.
There are different discussions about
but even without the actions, there is not even equations of motion. I think
Which
there are no both theorem with
Okay.
fair assumption. I don't. Maybe someone will find it.
Okay. Anyway, this is then our final slogan, that orientation memory is spin memory plus a local duality generator. And so that finally brings me to the conclusion where, first I'm going to just summarize what I just said so that you have sort of take-home message, and then say a bit more about some outlook. So the take-home message is that, as I said, some freely falling gyroscopes react to gravitational radiation, and they do so by precessing in a certain way relative to distant stars, and that leads to a net memory effect. In practice, I computed that by just computing the spin connection in a Bondi metric, and it was, remember that there was this idea of doing it in the source-oriented frame, rotating to the star-oriented frame, and the result, as we saw, was closely related to various gravito-magnetic components of the gravitational field. Now, a natural question that you might ask by way of a conclusion is, I started by talking about experiments, so you might wonder what's the real order of magnitude of this kind of effect. So let's just try to estimate it by using some elementary dimensional analysis. Remember that theta was the integral over time of a precession rate, and the precession rate itself was 1/r² times something that involves the shear. Now, it turns out that because the shear appears in the metric, you can see that it's a length. And oh, by the way, here, so far, I've always set Newton's constant to 1, speed of light to 1. So it turns out that shear has dimensions of length. Time is really, I guess, length over the speed of light. So in fact, this is a length squared. This is a length squared over r squared. It had to be, of course, because theta is dimensionless, so it had to be dimensionless. Yes, but it wasn't guaranteed that the shear had dimensions of length. That's actually the non-trivial consistency check that I just made here. You have to make sure that it could have happened that the shear would occur at subleading order in 1/r and would have dimensions of length squared itself. And then, this would have shown that I had somehow screwed up the computation. Here, at least, you're sure that you haven't. And also the length scale, by the way, has to be emphatically independent of the radius. So you have 1/r² behavior, which you can do nothing about. And the length scale has to be built out of some properties of the source itself. So the way you would proceed is to say, well, let me imagine that there is some mass scale in the source, and then let me use a mass, Newton's constant, and the speed of light to build an estimate for what happens. And it turns out that the only solution is something like this. So to make this a bit more telling in terms of astronomical units, you can rewrite this in terms of the mass of the sun and in terms of light years. And as you can see, this is completely tiny because there's a 10⁻30. And the seminal observations of gravitational waves typically involve orders of magnitude of 10 to 100 solar masses with distances of hundreds of millions of light years. So this is really way too small. For supermassive black hole mergers, actually, this is of order 1, this whole parenthesis. So you have an angle of 10⁻30, and I have no clue that's ever. It's smaller than the inverse of Avogadro's number. So no, I have no clue. In any case, I'm going to close on that and just mention some basic follow-up questions that you might address given this talk. The first is sort of a technical point. I focused on observers who are fixed, but that's sort of an unnatural restriction. Maybe you want observers who are boosted a bit. And that's actually a bit perhaps more interesting as a question than it sounds, because then you would have to compare this to the BMS transformation law of the covariant dual mass aspect, which is covariant, so it has to be the same thing. That's one thing you can wonder. Another question is, how good is this estimate? Can you actually use some more advanced estimates of how a binary system behaves to have a better sort of argument for how large this theta angle could be? This I really do not know. And finally, there's a question about what would happen if you were to do some gravito-magnetic monopoles, in which perhaps this average precession weight would be quantized or something like that. So there's a bunch of questions, and there's many others which are not mentioned here, which perhaps I hope to address someday. So in any case, I hope you've enjoyed this. I was at least very happy to talk to you about it. And so thanks very much for your attention.
Questions?
Yes, Monica.
So since this is very much related to this spin memory effect, like, can you compare? Is this more observable than so that was an effect where basically you had the time period, right?
Yes.
Are are they equally hard to observe, or?
They're really similar. As far as the order of magnitude, as far as I know, is similar, essentially because whatever signal you actually observe, it's very small. It's in any case, it's very weak, so you can focus only on the linear terms, and the linear terms are the same. It's just delta Q. That's the linear term that you find.
And that actually, what they're measuring is not really the time delay, but C times the time delay. They're looking at probably they will be looking at interference pattern. So then it's really the same 10 to the minus 5.
I think so. Yes. It should be related. I mean, the order of magnitude is sort of the same.
Isn't this the order of magnitude of what they measure at LIGO?
Is it?
I thought this interference.
That would be amazing.
Sensitive to something which is much smaller than the size of an atom.
That would be
I thought it
amazing.
was minus 20.
Yeah, minus 20. Oh, okay.
So, I mean, to be fair, here,
Getting closer.
if we're talking about an angle, and then, if you can somehow measure that angle over very large distances, you increase your sensibility. So maybe, maybe I'd be delighted if there was hope. That would be amazing. I really do not know. It's
You mean a very, very long gravitational wave?
No, I really mean like,
No.
I talked here about the gyroscope that you're carrying in your hand, but imagine that your gyroscope was, I don't know, 1 kilometer, an object which is huge with some, I don't know, lasers going all around the place. And
It's just a small gyroscope that shoots a laser beam.
Or you shoot a laser, exactly, and then you have to
A tiny change in the angle will make the laser beam far out.
Yes. So we've talked about this with Ali, and we don't dare to claim anything because we are theoreticians all the way, so we have no clue how these things are done. But yes, it's a very interesting question.
Of course, the goal is not to measure this effect, but to measure deviations. That if this effect is there, as you show in Einstein gravity, we don't.
Okay, fair enough. True. Yeah, then it's even more hopeless, probably.
Well, it's also good to verify that there is
a computational mistake.
Yes.
About your earlier question, I looked up at the talk by David Nichols, who has been making these proof of principle estimates for how the memory effect can be measured. And I think the claim is that the displacement memory effects, the linear one that was also can be measured at the end of this decade with advanced LIGO or with some future telescopes like the Einstein telescope or something called Cosmic Explorer. So they this is one of ours at least. So this is. You should talk to Strominger.
We talked to him. Well, we wrote to him, and he said he read the paper. So yes, we'll see. But indeed, as Andrea was pointing out, the displacement memory effect is leading in front of this higher effect. So if you want to observe memory, probably you would first bet on the displacement memory effect for sure. You wouldn't try to do this thing. That's it.
Probably a different way of deriving it would be to look at the soft behavior of scattering amplitudes and look for this logarithmic trends in that small energy. As a shock cell company we're doing.
Are you saying these effects that differ from the spin memory come from?
But first of all, I'm asking whether the spin memory effect was related to the soft behavior of amplitudes in this fashion.
So spin memory is
the log omega behavior of scattering amplitudes.
So what you're saying, this stuff by Sen, I think this comes from loop corrections. So soft, so the soft limit of amplitudes, but from loop correction.
But from soft loops.
But these are classical bits.
It's very classical. Yeah.
Yeah, but loops can also be classical.
Yes.
In terms of amplitudes,
so I'm asking whether you could distinguish the two effects, spin memory,
from some argument for
distributions in the soft behavior of amplitudes.
I do not know. I am aware, at least, of the literature that says that there is this link between the subleading soft graviton theorem and the superrotations, really. But even with superrotations, I mean, there's a question of what you call the superrotation. Here, I called it a superrotation. It was an area preserving diffeomorphism. But then, if you want to talk about superrotations in the original sense, local conformal transformations, it's a completely different set of transformations. It's not even a group. So, what exactly is related to what there? I think there is at least some amount of ambiguity in that. Partly because it's research in progress. I mean, there's a bunch of things that are being done every day. So one has to clean up what's being said. Yes.
No, just because you mentioned at some point that the spin memory effect that they were actually looking at different observers that were that there weren't inertial observers.
So, sorry, did you say?
You said, I thought you said that Pascal looked at a set of observers that were inertial.
Yes, actually an observer who is not inertial, who is just at rest in body coordinates. So at leading order, it doesn't change. At leading order, it doesn't change much, but there are many subleading corrections to the statement, and this is really a subleading effect.
Right.
So, for example, you find 1/r corrections in the spin connection. The spin connection has certain 1/r components which do not appear here, which you have to take into account. So the results are slightly different, even though there's one part of the formula that looks exactly the same.
But if you look at the same observer, it might have to, you're saying you even get different terms at 1/r, so you wouldn't know.
I mean, it's a different setup. They're looking at a non-freely falling observer. They don't talk about the tetrad to begin with, so it seems like they're using, I guess, in this language, you would say you're looking at an accelerated observer who is using a source-oriented frame. And so then your spin is, I guess there's this Thomas precession thing. So it's Fermi-Walker transported, and Fermi-Walker transport happens to give you this different spin connection, which has these 1/r effects. So it's really a different computation.
But if you are doing an experiment with a gyroscope in space or on Earth or something, you have to be the freely falling, right? So this is the one that you would
presumably. So we've had discussions also, Ali and I, about this. Are you freely falling? Are actually fixed? Here I'm saying freely falling with respect to this particular boundary metric, but an observer who happens to be in the, I guess, in the solar system, well, the metric is much more complicated. So how big is the effect of having the sun, which is here?
Yeah, you mean you're neglecting all the effect of the other perturbation to the flat metric, which are actually more important. So
I would say so. So are you really, in this language, are you freely falling? Are you, for all practical purposes, fixed in terms of those coordinates, even though you're actually freely falling in terms of the
by attraction of the sun?
Exactly.
Yeah.
So I do not, again, realistically, I don't know.
If I understand.
Sorry?
You have to walk more.
Exactly, yes.
Okay, I guess if there's
Thanks.
no other question, let's thank the speaker again.